Okay, so in this section, we're going to take a closer look at Ampere's law and see in what cases we are going to need to modify it. So we know from Faraday's law that a changing magnetic field produces an electric field. So by symmetry, we should expect a changing electric field to produce a magnetic field. So we're going to use Ampere's law to find a relationship between a changing electric field and a magnetic field. And we're going to be using the example of a charging capacitor to find this relationship. So here I have a situation where I have a charging capacitor. So these are the plates of the capacitor, and the current going through the circuit of this charging capacitor circuit. And I am going to now apply Ampere's law to find the magnetic field around this current carrying wire. So I have created an Amperian loop here. And what I've done now is I'm going to look and apply Ampere's law, but using two different surfaces. Okay, so in the first case, I have my Amperian loop, and I'm just looking at the surface that has the boundary of the Amperian loop, and it's just the plane surface here with I piercing through the surface. And so I enclose the I going through the surface with the boundary of the Amperian loop is just equal to I, the I going through the circuit. And that's what I've applied here. Now I'm going to use the same boundary, the same Amperian loop, but my surface is going to be kind of this bulged out, kind of like balloon surface that passes through in between the plates of the parallel plate capacitor. Now, if I look at the current, the I enclosed in this case for the same Amperian loop, but now a different surface, there is no current that passes through this surface too. And so when I apply Ampere's law, I get 0 for I enclosed, and therefore I get 0 for my magnetic field. So we have come up with a problem here because obviously there is a magnetic field here. We know that this is a current carrying wire, so there has to be a magnetic field around it. So we have found there's a problem with Ampere's law because we found a situation where we don't get the correct magnetic field. So the problem is that this version of Ampere's law only works for steady currents. For non-steady currents, like the current of a charging capacitor, we need to add an extra term to Ampere's law in order for it to be valid. The electric field between the plates of a charging capacitor is changing. Okay, so for the second surface where we're between the plates of the parallel plate capacitor, so what we're going to have to do is find an extra term in Ampere's law that expresses the fact that a changing electric field also produces a magnetic field. So we'll start by looking at our parallel plate capacitor. We know that for a parallel plate capacitor, Q is equal to CV, V the voltage between the plates, C the capacitance, and Q is the charge on the plates. We also know that V, our electric potential, is equal to the electric field times D, the distance between the plates. And we know for a parallel plate capacitor, the capacitance is equal to epsilon naught A, the area of the plates, over D, the distance between the plates. So we're going to plug in the capacitance and the voltage to get Q is equal to epsilon naught A over D, E times E. Cross out the D's, and we'll take the derivative with respect to time of both sides. I can take out epsilon naught, and then I have an EA. EA, if you remember, is just our electric flux. So I have dq dt is equal to epsilon naught dE phi E dt are changing electric flux. And I'm going to call this term, epsilon naught d phi dt, ID, a displacement current. So this is the extra term needed in Ampere's law. So now we have this version of Ampere's law that works fine if we're just dealing with steady currents. If we're dealing with a non-steady current situation like that of a charging parallel plate capacitor, we have to add this extra term, ID, which is equal to epsilon naught d phi dt. So we have I enclosed term, that's this current here, and then a term that comes from any kind of changing electric flux. So this term accounts for the magnetic field created by current, while this term accounts for the magnetic field created by a changing electric field. So now we can apply Ampere's law, this modified version, to the situation we had earlier, where we're looking at the charging capacitor with situation 1, surface 1. There is no changing flux for this electric flux in this surface, but there is an I enclosed. It's just equal to I. So we get B is equal to mu naught I over 2 pi r. That's what we should expect for the B field around a current carrying wire. Now for the second surface, same Amperian loop, but this bulged out surface. In this case, there's no current going through the surface, so the first term goes to 0, but there is definitely a changing electric flux going through the surface. So we get B 2 pi r mu naught epsilon naught dE A dt. And we know for a parallel plate capacitor, the electric field is equal to sigma over epsilon naught, or Q over A being the area of the plates. So it's the surface charge density over epsilon naught. So we can plug that in for RE. So we just get, after canceling out A's and epsilon naughts, mu dq dt, which is just our current. So we get the same answer for our magnetic field in the two situations, which we should, because it's the same magnetic field, even if we use different surfaces. So this modified version of Ampere's law, we can now use and get consistent answers even in non-steady current situations. And then you will be doing this example problem. And then I wanted to finish just by looking at everything kind of synthesized that we've learned. We have Gauss's law, where we take the electric field, its surface integral of the electric field, or the electric flux, is equal to Q enclosed over epsilon naught. The equivalent for magnetic fields, the magnetic flux through a closed surface is always 0, so that's no magnetic monopoles. And then we have Ampere's law, but modified, right? You have a current or a changing electric flux produces a magnetic field, and Faraday's law, a changing magnetic flux, gives you an electric field. So this set of equations together Gauss's law, electric and for magnetic fields, Ampere's law modified, and Faraday's law gives us Maxwell's equations. And Maxwell's equations give us a good kind of synthesis of electricity and magnetism. And from these equations, we can derive things like how electromagnetic radiation is generated. So we'll leave it there for now.